Okay, so let's continue our discussion. Okay, so we know like the expected this E can be put into the summation sign, right? So now, okay, remember, so if we denote, okay, the probability that there exists a node on the search path of Q that is created in iteration I, we denote it as Pi. Okay, this is the probability that a node, okay, exists on the search path of Q that is created in iteration I. Then, because we know, okay, in our previous discussion, okay, each time when you insert a node, at most, the depth will be increased by at most 3, right? Okay, so we know that if you look at this expected xi, it's bounded by 3 pi, because, well, at most when you add certain nodes into a search path, it's not going to be 3 times of that of the pi. Okay, so this is bounded by this. Okay, and then also, okay, we know iteration I contributes a node to the search path of Q exactly if this trapezoid, okay, that contains Q, okay, in the previous round, okay, is not the same as the trapezoid that contains Q. Okay, if these two are different, okay, then the iteration I will contribute a node to the search path, right? Because we must remove that trapezoid and then add something back, right? Okay, so the trapezoid containing Q in TS. Okay, this is a new one that contains, Q the Q in the new trapezoid. Okay, so we know, okay, the Pi represent the probability that, okay, this trapezoid, okay, that contains Q in the iteration I, okay, is not the same as the trapezoid that contains Q in the iteration I minus 1. Okay, so what situation you are going to have this? In what situation you are going to have this? Okay, when removing Si will result in the change of trapezoid that contain Q in Si. Here we try to think this issue in reverse order. Originally we tried to think about this, by adding a Si, right? By adding a segment. Now we try to think of this by removing a segment. When you remove a segment, okay, it will result in the change of trapezoid. What happened? What situation will cause that? Okay, only if this Si either contribute top, bottom, left P or right P of this trapezoid that contains Q in Si, right? And because now it's interesting part. Okay, now we need to make use of the randomized algorithm, the property of randomized algorithm property, because Si means this currently we have I segments. We already add I segments. Okay, so we know like the top, bottom, left P, right P. Okay, these 4 elements. Okay, well, so they could come from different sources, right? They could come from different sources, but all these I segments have equal probability to be either the top or bottom or left P or right P, right? So what the probability for the the SI, the segment, the I segment, to be the top of this trapezoid, okay, the probability is okay, because we, as I said, like because it's randomized algorithm, so every segment, we have I segments, right? So every segment will have the same probability to serve as the top of this trapezoid. Okay? And the probability for the SI to serve as a bottom is also I, 1 over I. And the probability for that segment to contribute left P is also, and for that for that segment to contribute right P is also 1 over I. So the total probability, okay, for removing SI, the I segment, will affect the trapezoid that contains Q will be, because these 4 cases are, disjoint anyway, right? Disjoint. So we just add them up. So it is, this probability is bounded by 4 over I. Okay? And then, okay, if we use the above formula, okay, now we have this expected, summation of xi will be smaller or equal to summation of 3pi. We already know that. And the pi, as I said, is going to be, each pi is going to be smaller or equal to 4 over I, right? So we can replace pi by 4 over I. So the summation becomes like this. It's smaller or equal to this thing. We can get a 12 out of this summation. So it's going to be 12 summation I 1 over I, where I start from 1 to n. You guys know how to do this, right? Assuming you have the n is large enough. So this thing is this is 12. This is harmonic series. Harmonic series is basically log n. Okay, so that's. So the query time is log n. Okay? So far so good? You guys still with me? Okay. Okay. We are running a little bit out of time, so let's talk about the worst case storage complexity. Okay. So we know total number of nodes, okay, for that data structure, that tree-like data structure, okay, will be the amount of space needed for the leaf node plus amount of space needed for the internal nodes, right? Right? Nobody could have any question about that, right? So we know the leaf nodes, okay, each leaf node represents a different trapezoid, right? Each leaf node is a different trapezoid, right? Okay, you can obviously see like the leaf node do not, the trapezoid is not duplicated, right? Okay, you may have like a trapezoid which is pointed by more than one parent, right? But at least that you don't see a trapezoid, to be duplicated in the leaf node, right? So we know the leaf node, the trapezoids, number of trapezoids is bounded by big O(n), right? We know it's like a 3n plus 1, right? Right? So we just, this is number of leaf node. Number of leaf node, big O(n). To be exact, it's bounded by 3n plus 1, but we just write it big O n, okay, plus, okay, the total number of internal nodes. So the summation I from 1 to n, the number of inner nodes created in iteration I, okay? So that's obviously the total number of internal nodes, right? So if you represent the number of new trapezoids that are created in iteration I, okay, as kappa I, okay, this is number of new trapezoids that are created in iteration I, okay. If you look at the insertion process, you will see that the number of inner nodes that gets created, I mean, when we create like a kappa I new trapezoid, I mean, the number of new inner nodes that we insert will be exactly kappa I minus 1. Why? I mean, if you do not believe, you can look at here. Okay, here we have 4 new, four new leaf nodes, right? So we have 3 internal nodes, right? And here we have how many? 1, 2, 3, 4, 5, 6. We have 6 new leaf nodes. How many internal nodes do we have? 1, 2, 3, 4, 5. But be very careful here. Okay, some internal nodes may represent the same thing. For example, here the Si is duplicated 4 times, right? But if this iteration is going to add kappa I number of leaf nodes, then the number of internal nodes that gets added will be kappa I minus 1. Okay, that's for sure. Okay, that's.
We consider the 4 nodes removed.
That's the interesting part. We don't consider that because let me put it this way. Okay, when you remove these 4 nodes, actually the storage is becoming cheaper, right? Because we are talking about the bound. Okay, so it's okay. It is okay. Oh, sorry, here. Okay. So worst case upper bound on kappa I, okay, follow from the fact that the number of new trapezoids in TSI, okay, in iteration I, okay, can obviously not be larger than the total number of trapezoids in TSI, which is linear to number of segments that are already in the subdivision. So, that's the worst case. Okay, the segment happen to go across all the trapezoid. Okay, I mean, actually, it's almost not possible. I mean, in many cases, but let's consider this worst case. Then it's going to be big O n plus big O I from 1 to n. I mean, you know this, right? I mean, that's where I say like, this analysis is not very mathematics, okay? Because normally you don't write formula like that in mathematics department, okay? Because big O I actually represent a set of formulas, not just one formula, okay? But you get idea, okay? We are in computer science, so I'm now in computer science, yeah. So I don't need to care about that formality. I mean, in mathematics, okay? So big O I start from 1 to n. Okay, if you add it up, it's going to be just like 1 plus 2 plus 3 plus 4 plus up to n. The result is going to be n squared. Okay, is this explanation intuitive enough for you? Okay, I know, like if you're in mathematics, you will hate this notation. This doesn't make sense, to be honest with you. But intuitively, I mean, hopefully, if you're in computer science, I mean, it should give you enough intuition. If you want the more formal analysis, you may need to check out the paper for this. Okay, so that's the worst case, right? I mean, for randomized algorithm, you can only analyze two situations. One is the worst case, one is expected case, average case. Okay, so let's again look at expected storage complexity. Okay, derivation. I mean, originally we don't like that slab situation. It's because the storage complexity was like n squared, right? Okay, so in some sense, like in the worst case, storage complexity is almost the same, right? But for randomized algorithm, we actually do not care that much about worst case complexity. We care more. I mean, I'm not saying worst case is not important. I'm just saying like average case is more important in randomized algorithm. So let's look at here. Okay. So similarly, okay, we have this one. The difference between this one and the previous one is that now we try to put the expected on the second term here. Okay, so here the expected, this one. I mean, original. I mean, it's kappa I minus 1, right? We already explained this thing earlier, right? Okay, so this kappa I minus 1. I mean, the summation. I mean, we can put for a similar reason, we can put this e into the summation, so it becomes like something like this. The constant, this minus 1 doesn't. I mean, it's not important. Okay, it's not important. When we do the analysis, okay, the order is the one that matters. Okay, a student came to me like during break. I mean, discussing about like the constant term in the time complexity. Remember, the constant term in complexity. Okay. No matter it's time complexity, storage complexity, those are not that important when we talk about algorithm. Okay. So we have this. Okay. So this one, okay, for a trapezoid, okay, and the segment S, okay, we define, okay, this delta, okay, function, okay, is okay. It is 1 if this trapezoid disappears, okay, when S is removed from Si, okay, then we denote this one as a 1. Otherwise, we denote this as a 0. Okay, then you try to, for every trapezoid and for every segment in Si, you do a summation over this delta function. It's going to be less or equal to 4 times of the total number of trapezoid in Si. Why? Because there are at most 4 segments that cause a given trapezoid to disappear. I already discussed that, right? Top, bottom, left, right, right? Okay, so the summation of this, okay, will be less or equal to 4 times of this. And we know this thing is linear to the number of trapezoids. Okay, we have I segments, right? So the number of trapezoids in this at this moment is linear to I, so it's big OI. Okay, and okay. Then again, if you are in mathematics department, please don't beat me up, okay? We use the above formula, okay? Expected value of kappa I will be, because it's average, right? This is average, right? So this will be, because we have I segment, and now we are using the idea of randomized algorithm. As I say, like every segment basically, have the similar effect. Okay, so we can divide the original listing by I, okay? Because as I say, all the segments. I mean, now we have I segments. All these I segments have equal, can be accounted for equal, amount of impact. So when you want to consider just one segment, the impact of one segment, so it's just divide the whole thing by I. So, well, it's going to be big OI divided by I. Again, this thing equal order 1. If you are in math department, you will beat me up. You will say this doesn't make sense. But at least, hopefully if you are in computer science, this give you enough intuition to understand each time when you add a segment, the expected number of internal node to be added is constant. It's a constant. Okay? So because of that, okay, so expected time to insert Si, okay, is big O kappa I plus the time needed to locate the left endpoint of Si in Tsi I minus 1, because we need to find the location of the left endpoint, remember, in order to do the insertion. So it's going to be order 1, okay, plus, okay, order 1 is originally when you put the whole thing into bounding box, and then plus, okay, summation I from 1 to n, you are trying to add it to add segments one by one. So each time it's going to be, this is the amount of time needed to do a search on the left endpoint, okay, of the new segment. So it's log I. We already proved that this is log, right? I mean, because we are considering the expected time complexes, expected complex here. So plus big O expected K kappa I, which is a constant. So the whole thing here, okay, is this part, because this is a constant, compared to this one can be ignored. So the summation big O log I is going to be big O n log n. Okay, so this is expected storage and construction time, okay, complexity. I mean, which others will be the same, okay, like this. Okay, so that's about it for the analysis. Hopefully, you guys are with me. If you are lost somehow, I'll be more than happy to discuss with you. But probably not probably after the class, or you can come to my office hour, okay? Because we only have about 20 minutes to talk about the rest of the content, okay? Because remember, we talk about general cases, right? Only. Now we need to talk about degenerate cases. I mean, what is degenerate case that we need to talk about? It's when some endpoints happen to have the same x coordinates, okay? Which can include two cases. The first case is, we may have vertical segments. Okay, vertical segment, of course, two endpoints will have the same x coordinate, right? Or, you have endpoints that come from the different, segment that have the same x coordinate, okay? And also, the query point, okay, may fall on a segment, okay? So how do we deal with this? Okay, last time, we used a composite number. If you remember, in the previous chapter, we talked about composite number, right? But now we don't use that, okay? Can we use composite number here to solve the problem? To be honest, we may be able to do that, but that's actually more complicated. Okay, the easier solution here is to use what we call symbolic perturbation. Okay, what is symbolic perturbation? Okay, you could imagine, okay, every point, okay, there, I mean, its x coordinate is moved to a little bit to the right based on its y coordinate. Okay, there's like a epsilon. Okay, this is it's kind of like a transformation, but we keep in mind we only do this conceptually. We never do it in really do this. Okay, we only do this conceptually. So what we are, this is the transformation. Okay, for original x, the point x and y, now it becomes x plus epsilon y and y. Okay, so you can imagine. Okay, this epsilon is a positive number, but it's very, very, very small. I mean, well, to be honest, as I told you earlier, this transformation is just, it's just conceptual transformation. I mean, we never really compute it anyway. So what value this epsilon is really not that important. It's really not important. Okay, we just assume it's a positive number, and this epsilon is a positive number, and it's very, very small. And also, because of the existence of this epsilon, okay, all the x coordinate of all the points will be different now. Okay, the real epsilon value is never required at the end. Smiling face. This is important, right? Obviously, I mean, if you need to do this computation, I mean, you'll be crazy. Okay, so this shear transformation preserves the following two things, which are important. Okay, the order of points in x coordinate. So if your x coordinate, if your 2 points, they have different x coordinate. Okay, I mean, after the transformation, their left and the right relation will still be the same. Okay, so the order of the points in x coordinate remains the same, and also the above or below relationship between a point and a segment will also remains the same. Okay, let me make it originally, if you have a vertical segment, because of this transformation, you can imagine this point. Okay, even though originally they looks like they have the same x coordinate, right? Because they have different y coordinate, right? Then after this transformation, this point will be on the right of this lower end point. Okay, because of this, the vertical line sort of get like a little bit, I should like incline to this direction. Okay, you get the idea. Okay. So the good thing about our algorithm, if you really think about that, no matter you are doing query, okay, or you are doing the construction of the algorithm, the good thing about our algorithm is that our algorithm never really need to compute the intersection of lines. If you need to compute the intersection of line, then yeah, the value of epsilon matters, right? You have to compute, because if you have to compute the intersection, then the epsilon, I mean, what's the epsilon value, will have impact to the intersection, right? But in our algorithm, really, we only have two operations that will be needed. Okay, the first one is given 2 points P and Q, we need to decide. Okay, Q lies to the left, to the right, or on the vertical line through P. Okay, that's the first operation we need in our algorithm. The second thing is, okay, given two endpoints P1 and P2, and a query point Q, okay, given a segment with P1, P2 endpoints, and a query point Q, we want to test if Q lies above, below, or on the segment. Okay? So, the first one should be obvious to you, like you don't need to compute the intersection, right? Okay, and you don't need the epsilon value at all to make this judgment, right? Okay, because basically you just compare their x coordinate value. If x coordinate value are different, then you just use that to make a decision. If they are the x coordinate value are the same, then you look at their y coordinate value. Whichever has a higher y coordinate value will be on the right side. Okay, you don't need to compute that epsilon value. Okay, the second one may be a little bit more complicated. So let's look at this. Okay, this is for the first case, operation 1. Okay, for two transformed points, P and Q. Okay, we need to determine the left-right relationship. Okay, so after transformation, it looks like this. Okay, xp plus epsilon yp, and xq plus epsilon yq, and yq. So if xp is different from xq, then basically we just use the value of x to determine the left-right relation. Okay. If xp is the same as xq, and yp and yq are different, then we just use yp and yq to determine their relationship, as I said earlier. Okay, you don't need the value of epsilon. Okay, and if xp, xq are the same, yp, yq are the same, then these 2 points are the same. Okay. Oh, by the way, okay, here, okay, we do not assume we have 2 points. It's impossible for 2 points to be at the same location. Okay, unless you are talking about query point. Okay, if it's true query point, of course you report it. If it's like line segments, the endpoints. What should I say? Like when you need to use this operation, you normally don't need to worry about, this case. 2 points are the same. Okay? So this is for operation 1. For operation 2, okay, given a line segment and a point, want to see if it's above or below, okay, something like that. Okay, so that segment, let's say the endpoints, okay, P1 is x1 plus epsilon y1, and the other endpoints x2 plus epsilon y2. We want to test whether a point, okay, this point Q, we call it x plus epsilon y, lies above, below, or on this line segment. Okay, so we just check the vertical line through this point, which will intersect this segment. Okay, so basically we just check this one. Okay, this will give us like if x is the same as x1, then we will have y greater or equal to y1. And if x is the same as x2, then y must be smaller or equal to y2. Okay. From here, we can break it to two cases. x1 equal to x2. In this case, basically, this segment is a vertical segment. Okay. And in that case, obviously, like if this in that case, this point must be, must be on this line segment, because when we need to see if a point is above or below, it must fall in the range of the point must fall into the range of this x range. Because remember, when you do a query, remember, when you need to check if a point is above a segment or below a segment, that segment must, the point must be above. So that point must be above the segment or below the segment. It's not going to be like this point is, is it's not on or below the segment. No. It will never occur. It will never happen. Okay. So if it's a vertical line, that point must be on the segment. Or if x1 is smaller than x2, well, it's a regular case. Just do it very easily. Okay. Again, you don't need the epsilon value at all. Okay. So, okay. So as I said, all endpoints of each segment will have to be transformed only conceptually. We don't really need to transform the points. We only transform them conceptually, okay? Because we actually do just assume there's an epsilon value. To make like all the endpoints, the x-coordinate value are different. Okay, so the query point will also need to be transformed, obviously. Okay, in order for this the whole process to be correct. Okay, and the face of each trapezoid can be found by looking at the associated face of the top segment. Okay, or associated face of the bottom segment. Either way, it should be fine. Okay, so this is basically the last part of this chapter. Okay, so we are done with this question. Okay, and I have homework here, but don't worry about this homework. Okay, well, if you want to start early, you can use this one. Okay, to do the third homework. But as I say, I will assign third homework next week, not this week. Okay, so don't worry about this. Okay, and also, okay, I think like it's about time to talk about midterm. Okay, it's about time to talk about midterm. I plan today is what time is today? What day is today? It's 16th, right? So 3 weeks from today, the third week from today, the third Wednesday from today, okay, not the next one, it's the third one. So which will be April 6th. 哎，寒假？放假吗？哦 ，It's a break。我还不知道我们这堂课有机会放到假，赞啊，好吧，那 So you want to do it like 1 week earlier? Is it too? Or you want to?
The third assignment should be handed in.
I don't think we'll be able to give you back the third assignment before the midterm, because as I said, like I would normally give like 2 weeks for the homework, right? So it's not going to be. How about this? Like let's April 13th. Is that okay? April 13th. So let's do the midterm on April 13th. Okay? Will be okay? It's about a month from now. Okay? So I will try to cover 2 more chapters for the midterm. Okay? Because excluding 1 break, right? We still have 2 more weeks, right? If I can do it, I will do 2 more chapters. If I cannot finish another chapter, at least hopefully the midterm will cover 6 chapters. Okay? So any question?
So the midterm will not follow the range of our assignment.
Will not follow the range of the assignment. The assignments are good references. Okay, I will give you like I will see if I can get like the past midterm and use that as a sample midterm for you. Will be good. Will be good enough. Okay, I will post the sample midterm to the EE class. Okay, so you can get an idea like what the midterm will look like. Okay. Okay. So any
So you will you give us the assignment 3 or?
Yeah, I will give out assignment 3 before the midterm. Yes.
How about the result of
Assignment 3 result. You mean like return the midterm back to you guys? I'll probably not be able to do that before the midterm. Okay, but I will make sure that the TA at least give you the graded midterm homework 1 and homework 2. Okay, and of course, if you have any question with the homework, feel free to talk to me. Don't talk to the TA because TA may not be able to help you that much. Okay.
So we are going to midterm without our assignment.
Without assignment.
Without our assignment return.
I mean, you will get the first and the second assignment returned, but not the third one because I don't think, the TA will be able to finish that in time. Let me put it this way, okay? The third assignment, the due date will be after the midterm. Think about it, or like just right on the midterm, because it's 2 weeks after the assignment, right? After the assignment is given, so it will be, I think it will be right on the date of the midterm. How can I give that back to you? Okay.
I believe it will be on 1 week before the meeting.
No. Let me think.
Because
Yeah, but only 1 week. I don't know. Like because the week before that is a holiday, right? Think about that. The TA also need a break. Okay, I cannot ask them to work overtime. I'll be sued by the government. Yeah. But if you have any question for your homework, talk to me. I'll be very happy to help.
So the range of midterm will went to homework 4 or 5.
What's your question? Sorry, I don't get you.
Say the range of midterm will cover 6.
The first 6 chapters. As for whether or not to cover the 7th chapter, let me see. Okay, let me see. I hope to cover 6 to 7 chapters for the midterm. Okay, but whether or not I can finish 7 chapters, I'm not sure. Let me put it this way. Okay? Does that answer your question?
I have candidate explain my question.
Talk to me after class. Okay. So any other question? If no question, that's about it for today. Okay? What time is it now?